Hi everyone, my name is Aaron Nguyen. I am in Mr. J's Period 3 Physics Honors class, and because we have less than 3 to 4 weeks left until our midterms, I decided to do a screencast that tied in with some of our previous knowledge in physics and tying it to some real-world application. Specifically in this case, it is how NBA player LeBron James' three-pointer ties in with all the material we have learned in physics honors. So, the video itself.
LeBron will send it in for the Heat. Wade looking for the alley-oop, couldn't get it. LeBron on the spin, back to Chalmers. Wade to LeBron, a three to tie. Come on!
He waited on the pass. Good job by the Heat. They took the three, but they really weren't looking for it. They were looking for the first good shot they could get. They looked to the lob first. Then they ran their offense, and it wound up with LeBron in the right corner. He buried it. Now the Heat need a stop with 10.2 seconds left.
11 fourth-quarter points for LeBron James. That was his first three tonight, number 31 on the year. Tony, what's the first option? It was the last option.
No, you're right.
Alright, so I'm sure you guys get the basic gist of the video. You know, LeBron makes a three, and that ties in with our projectile motion stuff that we learned throughout the year. So our given conditions start with that the shot lasts approximately 1.3 seconds on the clock. It leaves his hand at 12.2 and touches the top of the rim at 10.9, so that's a total of 1.3 seconds. The distance from the three-point arc to the hoop is 7.24 meters. The height of a basketball hoop is 10 feet, or 3.05 meters, and LeBron James himself is 6'8", or 2.03 meters tall, with a vertical of 40 inches, or 0.106 meters. We have these two given equations here because we learned this a couple months earlier, and we are going to use these to find out all the unknown variables within this application. So you have the horizontal equation. X sub t equals x sub 0 plus cosine theta v sub 0 t plus 1/2 at squared. Now, if we assume that LeBron starts at a position of 0 meters and that he's sending the ball 7.24 meters, then the end result here is 7.24 with the beginning at 0, which is why we can cross that out because anything plus or minus 0 is insignificant. We do not know cosine, the angle, or the original velocity, so we'll just leave those as variables. And then we have the original time, which is 1.3 seconds, and then we add 1/2 no acceleration times 1.3, which is the second squared, and anything times 0 is also 0, so this can also be crossed out as it's insignificant. Therefore, we can simplify the equation to 7.24 meters equals 1.3 cosine theta v sub 0. With a little bit of number messing around, we eventually get to the idea that 7.24 divided by 1.3 is equal to cosine theta v sub 0, and when we square both sides, as we do in the next line, 7.24 divided by 1.3 squared is equal to cosine squared theta times v sub 0 squared. And then you move around the numbers, figure out what this value is, and then you have v sub 0 squared equals this 31 point, all these other decimal places, divided by cosine squared theta. Now this is the main equation we will be working with. And so then we move on to the vertical equation. It's the exact same thing as the horizontal equation, it's just that we switch from cosine to sine, and then we plug in the numbers, and then with a few number jumbling, we get 9.1994 equals 1.3 sine theta v sub 0. Now, this requires some trig identities. Because sine squared theta plus cosine squared theta is equal to 1, sine squared theta equals 1 minus cosine squared theta. Thus, sine theta equals the square root of 1 minus cosine squared theta. Using that knowledge, we can plug sine in with this. So we get 9.1994 equals 1.3 times the square root of 1 minus cosine squared theta times v sub 0. And then we can move around the numbers a bit. And then when we square both sides, we get this quantity, this fraction, squared, equals, because we got rid of the radical by squaring it, the quantity of 1 minus cosine squared theta times v sub 0 squared. Thus, when we move things around, v sub 0 squared equals 50.0 all that stuff, which is the fraction evaluated, divided by 1 minus cosine squared theta. Now we have two expressions that tell us what v sub 0 squared is. So when we take these, we evaluate them, and set them equal to each other, we get 31.016, all these numbers, times 1 minus cosine squared theta equals this, evaluated with cosine squared theta. Now, by distributive property, we can move this stuff into, and expand it into 31 point that minus 31 point that cosine squared theta equals the other side. And then that way, when we move them around, we finally get 31 point all that equals 81.09, etc. times cosine squared theta. And from here, it's simple algebra. We get cosine theta equals the square root of this fraction, and then we evaluate that, and by using the inverse cosine, we get that theta equals 51.80 degrees. This is part 2 of our combining the two. Because theta equals 51.80 degrees, we just take the previous expression, v sub 0 squared equals this, and then we plug in theta, and then our velocity becomes 9.01 meters per second. So what exactly does this mean? In the strictest sense possible, it means that if you're 6'8" and have a vertical of 40 inches and you want to shoot a three-pointer, then all you have to do is aim the ball at a 51.8 degree angle and release at an initial velocity of 9.01 meters per second. Obviously, this isn't as applicable to us, but when we think about it, we can get a general estimate of what velocity and what angle we'll need if we are to play basketball ourselves. So this is our proof that it works. Using these conditions, velocity equals 9.01 meters, theta equals 51.8 degrees, delta xh, which is the change in change in position horizontally, which is the distance from the three-point arc to the hoop, is 7.24 meters, and delta xv, which is the vertical change, is almost 1 meter, 0.09184, which is the difference between the height of the hoop and LeBron's height plus vertical, which we assume is the release point. Using all of this, we can use the simulator we have in class and then plug in the numbers. Since the angle is 51.80 and the initial speed is 9.01, the mass we can assume is, the mass itself is irrelevant, and considering the distance, the vertical distance, 0.092, which is close enough to 0.9184, and this here is measured at 7.24, which is close enough. And then given these conditions and we fire, we see that it hits the target exactly. And this is how we can use physics to calculate how three-pointers and other shots tie in with our physics honors knowledge.